Welcome to Science, to Sleep By, where the mysteries of the cosmos drift through your mind like starlight, carrying you into a world of calm discovery and deep rest. Tonight, we travel to the edge of everything we know, to the silent frontier where space itself stretches, where galaxies drift apart in an endless dance of time. Our question is both ancient and infinite. When will the universe stop expanding? Since the dawn of existence, space has been growing, breathing outward from that first cosmic spark we call the Big Bang. But how long will it last? Will the stars ever stop receding? Will gravity ever pull the universe back into itself? Or will expansion go on forever, until everything fades into a quiet sea of cold and darkness? As you close your eyes, imagine the universe as a gentle pulse, galaxies flowing outward like ripples on a vast cosmic ocean. Tonight, we'll follow those ripples back through time, through the birth of the universe, through the discovery of dark energy, and into the distant future that awaits all things. So settle in, take a deep breath, and let the sound of the universe, ancient, endless, and expanding, guide your thoughts into peace. This is Science to Sleep By, and this is the story of when the universe might stop expanding. Imagine, for a moment, absolute silence. Not the quiet of a still night, not the hush that falls after a storm, but a silence more complete than anything you have ever known. No space, no time, no light or sound or breath, only the possibility of everything that would one day exist, compressed into something smaller than an atom, smaller than imagination itself. This was the beginning before beginnings, the state before the birth of the cosmos, and from this unimaginable stillness, something extraordinary happened. The universe awoke. In an instant that we can only describe but never fully picture, the universe burst into being. It wasn't an explosion in space because space itself did not yet exist. It was the expansion of space, the sudden swelling of reality from a point of infinite density and temperature, what scientists call the singularity. It happened roughly 13.8 billion years ago, a number that carries the weight of eternity. And in that first moment, everything, every star, every planet, every atom that would ever exist began its long journey outward. The Big Bang was not a sound, though the name might make it seem that way. There was no boom echoing through the void. There was only the creation of space and time, unfolding faster than light, a surge of energy becoming matter, matter becoming form, and form eventually becoming everything we know. It was as if reality took its first breath, a breath that would never end, expanding, cooling, and giving rise to the grand cosmic symphony that surrounds us tonight. For the first tiny fraction of a second, what physicists call the Planck time, less than a trillionth of a trillionth of a trillionth of a second, the universe was a storm of unimaginable energy. Temperatures soared beyond what any star could reach, densities crushed beyond measure, and yet, in that chaos, the rules of nature were written. Gravity, electromagnetism, and the nuclear forces that hold atoms together all took shape. The universe was setting its own laws, like a composer finding the first notes of a melody that would play for billions of years. As the universe expanded, it began to cool. Energy condensed into particles, first quarks and gluons, then protons and neutrons, and finally, after mere minutes, the first atomic nuclei were born. Hydrogen and helium, the simplest elements, filled the young cosmos like the first ingredients of a vast recipe. And with them came the possibility of light. At this point, the universe was still opaque, a thick, glowing plasma of particles and radiation. Photons could not travel freely. They were trapped in a dense fog of matter and energy. It would take nearly 380,000 years before the universe cooled enough for electrons to settle into stable orbits around nuclei, creating neutral atoms. When that happened, the fog lifted, and light broke free for the first time. Those first rays of light are still traveling through space today, stretched and softened by billions of years of expansion. We call it the cosmic microwave background, the faint afterglow of the universe's birth. A whisper of light that carries the memory of the first dawn. If you could close your eyes and somehow see that ancient moment, you would not see stars or galaxies. The universe then was smooth and uniform, a soft glow of light spreading in every direction. but tiny fluctuations, little ripples in density, one part ever so slightly thicker or thinner than another, began to form. These ripples were the seeds of everything to come. Over millions of years, gravity would take hold of these small differences, pulling matter together into clumps, those clumps into clouds, and those clouds into the first galaxies. In that sense, the birth of the universe wasn't just one moment, it was a process that unfolded over cosmic time. From that first spark of expansion to the formation of stars, the early universe was like a child growing, learning the rules of its own existence. Stars ignited, burning hydrogen into helium, creating heavier elements deep within their fiery hearts. When those stars died, they scattered those elements across the universe, making the building blocks for planets, oceans, and life itself. Think of that for a moment. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, all of them were forged in the hearts of ancient stars that lived and died billions of years ago. You are, quite literally, a product of cosmic expansion, living piece of the universe still unfolding. The moment the universe was born is also, in a way, the moment you began, because without that expansion, without that initial burst of creation, nothing that you see, feel, or love could ever exist. The question of what caused the Big Bang remains one of the deepest mysteries in science. Some theories suggest it might have emerged from a quantum fluctuation, a random spark in a pre-existing field of energy. Others imagine that our universe might be just one of many, bubbling into existence from a greater cosmic sea, each expanding on its own timeline. But what all these ideas share is a sense of awe, that everything, from the smallest grain of sand to the largest galaxy, began with an act of creation beyond comprehension. When astronomers look deep into space, they are looking back in time. The farther a galaxy is, the longer its light has traveled to reach us. The Hubble Space Telescope has shown us galaxies whose light began its journey billions of years ago, when the universe was only a fraction of its current age. Each of those galaxies is a snapshot of history, a glimpse into how the universe looked when it was young. To study them is to peer into our own cosmic childhood, to trace the steps of creation back toward that first radiant moment. And yet, even with all our knowledge, there is still a gentle mystery surrounding the beginning. Science can describe how the universe evolved from a fraction of a second onward, but the exact instant of birth, that first spark of expansion, remains hidden behind a veil of mathematical infinity. It's a reminder that some parts of existence may forever lie beyond our reach, and perhaps that's fitting. The universe, after all, is not only a place to be measured, but a story to be felt. So as you lie here tonight, listening, imagine that first moment. A darkness without edges. A silence so vast it could swallow thought itself. And then a shimmer, pulse, the first ripple of being. The universe expanding outward, carrying within it the potential for light, for life, for you. Each heartbeat you feel now echoes that same rhythm. The quiet persistence of creation that began nearly 14 billion years ago and continues even now. As galaxies drift farther apart in the silent tide of space, the moment the universe was born was not the end of stillness, but the beginning of motion. Not the end of mystery, but the start of an infinite unfolding. Every particle, every beam of light, every breath of air you take has traveled through that long journey of time, a part of a story that began when time itself was new. And somewhere in that vastness, the question lingers softly in the fabric of space, not just how the universe began, but where it is going, and what it means for the expansion to never stop after the first breath of creation. The universe began to stretch. It wasn't like an explosion hurling fragments through pre-existing space. It was space itself that expanded, carrying galaxies, stars, and light along with it. Every point in the universe moved away from every other point, not because it was flying outward, but because the fabric of reality was growing. This expansion, set in motion at the very dawn of time, would become the silent rhythm of existence, an invisible tide that still shapes every moment, every distance, and every corner of the cosmos. At first, the expansion was unimaginably fast. The universe grew from smaller than an atom to larger than a galaxy in less than a fraction of a second. Scientists call this mysterious period cosmic inflation, a moment when the universe swelled exponentially, smoothing out the wrinkles in energy and setting the stage for everything that would follow. Imagine stretching a tiny, crumpled balloon until it becomes vast and smooth. The wrinkles vanish, and what remains is the uniform, flat expanse we now observe across the cosmos. This inflationary period ended almost as quickly as it began, but its effects still echo in the pattern of galaxies and the faint glow of the cosmic microwave background that surrounds us like a soft, ancient light. After inflation slowed, the universe continued to expand at a gentler pace, cooling enough for particles to form atoms, and eventually for gravity to begin its quiet work. Tiny variations in density, those little ripples seeded in the early moments, began to grow under the pull of gravity. Over millions of years, matter collected into vast clouds, then into the first stars, and later into galaxies. These galaxies were like islands of light forming in an ocean of dark space, each one glowing with the energy of countless suns. But the expansion didn't stop. Even as galaxies formed, they continued to drift apart, carried by the same invisible stretching of space that began with the Big Bang. To an observer, then, if such a being could exist, the night sky would have been alive with forming galaxies and glowing nebulae. Yet slowly, imperceptibly, everything was moving away. The cosmic fabric kept expanding, and with it, the distances between everything grew. For billions of years, astronomers on Earth, long before humanity even existed, would have seen a different sky. If you could travel back in time and look at the night heavens as they appeared billions of years ago, you would see galaxies closer together, brighter, more numerous. The Milky Way itself would not yet have fully formed. Stars were being born at a furious rate, and the universe shone more brilliantly than it does now. But across those ages, the space between galaxies widened, and the universe began to dim, like a great fire burning low. The story of how we discovered this cosmic expansion begins not in the early universe, but in the early 20th century on a mountaintop in California, where a man named Edwin Hubble pointed a telescope at the stars and made a discovery that changed our understanding of everything. Hubble observed distant galaxies and noticed something strange. Their light was shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs because light waves stretch as they travel through expanding space. Just as sound waves stretch and lower in pitch when a siren moves away, at t first. Astronomers weren't sure what this meant. Some believed that galaxies were moving through space, flying apart like shrapnel from an explosion. But as more data came in, a new picture emerged. Not that galaxies were racing through space, but that space itself was expanding, carrying galaxies along like raisins in a rising loaf of bread. The raisins aren't moving within the dough. The dough itself is expanding, increasing the distance between them. In the same way, galaxies are mostly stationary in their local regions, yet the universe around them grows, increasing the vast distances between clusters and stars. Hubble's discovery confirmed what theorists like Georges Lemaitre had predicted. The universe was not static. For centuries, many scientists had believed that the cosmos was eternal and unchanging. Even Albert Einstein, when he first developed his equations of general relativity, was puzzled by what they implied, that space and time were dynamic, not fixed. To preserve the idea of a steady universe, he added a mathematical constant to his equations, known as the cosmological constant, to counteract the effects of gravity and keep the universe stable. But once Hubble showed that the universe was expanding, Einstein reportedly called that constant his greatest blunder. What he thought was an error, however, would later become one of the most essential clues to understanding the universe's fate. As astronomers began to measure the rate of this expansion, they realized something extraordinary. The farther away a galaxy was, the faster it seemed to be receding from us. This relationship, that distance is proportional to velocity, became known as Hubble's law, and it gave scientists a way to estimate the age and scale of the universe. By measuring how quickly galaxies move apart, They could essentially run the clock backward to a time when everything was once together, the moment of the Big Bang. But what's most remarkable is how subtle this expansion really is on human scales. The space between you and your desk isn't stretching. The distance between Earth and the Moon doesn't change because of it. Gravity binds planets, stars, and galaxies tightly enough to resist the pull of expansion locally. The stretching of space only becomes noticeable on the largest cosmic scales between galaxies separated by millions of light years. Over those distances, the expansion becomes evident. And light itself carries the evidence of that ancient movement. Every photon from a distant galaxy that reaches our telescopes tonight has been stretched by the expansion of space. Its wavelength elongated, its color shifted, its energy softened by billions of years of travel. The universe itself has stretched that light and in doing so, has recorded its own history within the fabric of time. When astronomers measure the redshift of a galaxy, they are reading the story of expansion written in light. Even now, this expansion continues. Galaxies drift apart, clusters become more distant, and the great web of cosmic structure, the vast network of galaxies and dark matter stretching across the universe grows thinner. Yet, within galaxies, stars continue to orbit, planets continue to spin, and life continues to thrive in small, warm corners of a cooling cosmos. It's a strange balance. The universe grows larger, but our local world remains intimately bound, untouched by the vast forces that stretch space itself. Over time, scientists have refined their understanding of this cosmic expansion using tools far more precise than Hubble's telescope. Satellites like WMUP and Planck have measured the faint afterglow of the Big Bang with exquisite detail, allowing astronomers to calculate the current rate of expansion, the Hubble constant, and the proportions of matter, and dark energy that shape our universe. What they discovered was unexpected. The universe is not just expanding, it's accelerating. Instead of slowing down under the pull of gravity, as most scientists once assumed, the expansion began to speed up billions of years after the Big Bang. Something unseen, something mysterious, seems to be pushing the galaxies apart faster and faster. This invisible force is what we now call dark energy, and it makes up roughly 70% of everything that exists. But the acceleration of expansion belongs to a later part of the story, a mystery still unfolding in the darkness of space. For now, what matters is that the expansion itself, the stretching of space that began in the first moments, continues quietly, invisibly, and irresistibly. It shapes the light of distant galaxies, the silence between stars, and the deep, cosmic rhythm that underlies existence itself. If you could somehow step outside the universe and look at it as a whole, you wouldn't see galaxies flying through space. You would see the fabric of reality itself expanding, like an endless ocean, swelling in every direction. Every second, the distances between the farthest galaxies increase. Every second, more of the universe slips beyond our view. The horizon of what we can see grows dimmer as light from the most distant places is stretched into invisibility. And so, as you rest and let your thoughts drift, picture this grand, slow motion. Galaxies like lanterns floating on the surface of an infinite sea, drifting apart, not through the water, but because the water itself is rising. That is the nature of our expanding universe, the silent unfolding of space, the cosmic tide that began long ago and continues even now, carrying all of existence gently outward into the unknown. For much of the 20th century, astronomers believed that the universe's expansion, first revealed by Edwin Hubble, was slowing down. The logic seemed simple and solid. Gravity pulls things together, and with so many billions of galaxies filled with stars and matter, the mutual gravitational attraction of everything should gradually slow the cosmic expansion that began with the Big Bang. The universe, it was thought, might continue expanding forever, but at an ever-decreasing rate. Or perhaps, if gravity were strong enough, it would someday halt the expansion entirely and begin to contract, leading to what was called the Big Crunch. For decades, that was the quiet consensus. The universe was expanding, but the rate was expected to decline over time. Then came one of the most astonishing discoveries in the history of science. A revelation so strange, so unexpected, that it forced humanity to rewrite the story of the cosmos itself. The discovery of dark energy began with the careful observation of dying stars, the kind known as Type Ia supernova. These particular supernova are unique because they explode with a consistent brightness, making them excellent standard candles. By comparing their apparent brightness to their known intrinsic luminosity, astronomers can determine how far away they are. In the late 1990s, two independent teams of researchers, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to use these cosmic beacons to measure the rate at which the universe's expansion was slowing down. But when they analyzed the data, the results defied every expectation. The supernova appeared dimmer than they should have been, farther away than expected. The universe, instead of slowing its expansion, was speeding up. Space itself was stretching faster and faster over time. It was as if some invisible force, stronger than gravity, was pushing everything apart. That mysterious force became known as dark energy, a term that captures its nature perfectly, unseen and detectable by direct means, and yet influencing the fate of the entire universe. To this day, dark energy remains one of the greatest mysteries in cosmology. Scientists can describe its effects, but not its essence. We can measure what it does, accelerating the universe's expansion, but we cannot yet explain what it is. When the discovery was first announced in 1998, it shocked the scientific world. Some astronomers resisted the idea, searching for possible errors in measurement, dust clouds obscuring light, or alternative explanations for the faintness of the supernova. But as more data poured in from space telescopes, galaxy surveys, and observations of the cosmic microwave background, the evidence became undeniable. The universe's expansion was not just continuing, it was accelerating, and it had been doing so for billions of years. This revelation changed everything. For the first time, scientists realized that the familiar matter, stars, planets, gas, dust, even the dark matter that holds galaxies together, makes up only a small fraction of the universe. Roughly 68% of the cosmos is composed of dark energy, 27% is dark matter, and less than 5% is the ordinary matter that forms everything we can see and touch. The vast majority of the universe, in other words, is invisible, untouchable, and deeply mysterious. To understand how dark energy works, imagine space itself as a flexible fabric. When Einstein developed his theory of general relativity, he showed that mass and energy warp this fabric, creating what we experience as gravity. Planets orbit stars, and stars orbit galaxies, because they are following the curved pathways shaped by the bending of space-time. But Einstein's equations also allowed for another possibility, that space itself could have an inherent energy, a property of the vacuum that could cause it to expand. Einstein had originally introduced this idea in the form of the cosmological constant, a term he added to his equations to make the universe static, because he believed, at the time, that it must be unchanging. When Hubble's discovery of expansion came to light, Einstein removed the constant, thinking it unnecessary. But decades later, with the discovery of dark energy, scientists realized that Einstein's discarded idea might have been correct after all. The cosmological constant could be a mathematical representation of dark energy, the energy of empty space itself. This concept is both simple and profound. If the vacuum of space has energy, then as space expands, more vacuum is created, and thus more energy is added. This energy doesn't dilute like matter does when it spreads out. Instead, it remains constant per unit of space, meaning that as the universe grows, the total amount of dark energy grows too. That is why the expansion accelerates. More space creates more dark energy, which in turn causes even more expansion. An ever-strengthening feedback loop written into the very fabric of reality. Still, this explanation, while elegant, leaves us with deep questions. What is the true nature of this energy? Why does it exist? Some scientists suggest that dark energy might be related to quantum fluctuations, the tiny, momentary appearances and disappearances of particles in empty space predicted by quantum mechanics. Others think it might be a new kind of dynamic field that changes over time, something like the quintessence imagined in ancient philosophy, a fifth element beyond earth, air, fire, and water, now reborn in modern cosmology. Whatever dark energy is, it dominates the universe's behavior on the largest scales. It determines not only how galaxies move apart, but also how the future of the cosmos will unfold. If its strength remains constant, the universe will continue expanding forever, growing colder and darker as stars burn out and galaxies drift beyond one another's reach. If dark energy increases with time, it could lead to the Big Rip, a scenario in which space expands so violently that it eventually tears apart galaxies, stars, planets, and even the atoms themselves. And if, by some unknown mechanism, dark energy were to weaken or reverse, the universe might someday collapse back into a fiery end. The discovery of dark energy did not just change science, it changed perspective. It reminded us that even in an age of precision and knowledge, the universe still holds mysteries vast enough to humble us. What we can see, all the light that fills our telescopes, is only a fraction of the story. Beyond that light lies an ocean of invisible influence, a quiet pressure that defines the shape and destiny of all things. In the decades since its discovery, astronomers have used every tool available to probe dark energy. The Planck satellite, the Dark Energy Survey, and telescopes like the James Webb Space Telescope are all part of humanity's effort to map how the universe's expansion rate has changed over time. By measuring the faintest flickers of ancient light, scientists can trace the cosmic acceleration and look for signs of change in the strength of dark energy. If it evolves over time, it might point to new physics beyond Einstein's theory. If it remains constant, it strengthens the case that it truly is a cosmological constant and unchanging property of space itself. Every observation so far supports one remarkable fact: the universe is growing faster with every passing moment. Galaxies that are now visible will one day slip beyond our cosmic horizon, their light stretched to invisibility by expansion. Billions of years from now, a distant civilization looking at the night sky might see only their own galaxy, surrounded by darkness, unaware of the vast cosmic history that preceded them. In that far future, the accelerating universe will isolate every island of stars in its own bubble of existence. The great cosmic web will dissolve into scattered fragments, each alone in an ocean of silent expansion. To think of this is both haunting and beautiful, that the same invisible force responsible for the universe's birth continues to drive its evolution, that the energy of emptiness shapes the fate of everything. Even now, as you listen and imagine the quiet drift of galaxies, dark energy is at work. It flows through the fabric of space around you, pushing the distant stars ever farther away. You can't see it or feel it, but it is there, a constant, gentle pressure that defines the boundaries of the universe itself. The discovery of dark energy reminded us that the cosmos is not static, not predictable, not entirely within our grasp. It grows, changes, and expands in ways that defy our expectations. And though we may never fully understand the force that drives it, we are a part of its story, of the same matter that drifts through the same space, living within the same expanding fabric of time. Dark energy is not merely a scientific puzzle. It is the quiet pulse of the cosmos, the invisible rhythm that carries galaxies apart, the soft, endless unfolding of everything that exists. To understand where the universe is going, we must first understand how fast it's moving, and that simple question, how quickly the universe expands, has guided decades of astronomical observation. Measuring the rate of expansion isn't like clocking the speed of a car or timing the rise of a tide. It means deciphering the rhythm of the cosmos itself, tracing light that has traveled for billions of years, and reading the ancient record written into the structure of space. The universe does not reveal its pace easily, but over time, through patience and the quiet labor of observation, scientists have learned to listen to its subtle pulse, the heartbeat of cosmic expansion, the first step toward measuring that Cosmic rhythm came from the realization that light carries the memory of motion. When a galaxy moves away from us, the light it emits is stretched by the expansion of space, causing its wavelengths to lengthen and shift toward the red end of the spectrum. This is known as redshift, and it is one of the most important tools in cosmology. By measuring how much a galaxy's light has been redshifted, astronomers can determine how fast it is receding. The greater the redshift, the faster it moves away and the farther back in time we are looking. And when Hubble first used this principle to show that the universe was expanding, but measuring exactly how fast a quantity known as the Hubble constant has proven far more difficult. The Hubble constant defines the rate of expansion today, how many kilometers per second galaxies move apart for every megaparsec of distance between them. On paper, it seems straightforward. In practice, it has become one of the most debated numbers in modern science. There are two main ways to measure it, and each tells a slightly different story. One approach looks outward, measuring the redshifts of distant galaxies and comparing them to their distances as determined by cosmic standard candles. Objects of known brightness like Type Ia supernova or variable stars known as Cepheids. The other approach looks backward in time, using the afterglow of the Big Bang, the cosmic microwave background radiation, to calculate how the universe must have evolved to reach its current state. When the European Space Agency's Planck satellite mapped the cosmic microwave background in exquisite detail, it provided an estimate of the Hubble constant based on the universe's behavior nearly 13.8 billion years ago. That number was precise, elegant, and deeply rooted in theory. Yet, when astronomers on Earth measured more recent cosmic distances using supernova and Cepheid variables, they consistently found a slightly higher rate of expansion. The two methods disagree not by much, but enough to raise profound questions. This Hubble tension, as it's now called, might be a clue that something fundamental is missing from our understanding of the cosmos, perhaps even pointing to new physics beyond our current models. Measuring expansion requires more than one technique. Over the years, astronomers have developed what they call the cosmic distance ladder, a hierarchy of overlapping methods that build upon one another. The first rung involves nearby stars, whose distances can be measured directly through parallax, the small shift in position that occurs when Earth moves around the Sun. From there, astronomers use Cepheid variable stars, whose brightness oscillates in a predictable way that correlates with their intrinsic luminosity. These stars serve as beacons across our galaxy and into neighboring ones. Beyond that, Type Ia supernova act as standard candles that can be observed in far more distant galaxies, allowing us to trace the expansion out to billions of light years. But even these luminous markers are only part of the story. In recent decades, astronomers have turned to even grander cosmic patterns, the distribution of galaxies themselves, as a ruler for measuring expansion. This method relies on something called baryon acoustic oscillations, faint ripples left in the matter of the universe by sound waves that traveled through the hot plasma of the early cosmos before it cooled and formed atoms. These ancient sound waves froze into the large-scale structure of the universe, leaving behind a faint, repeating pattern in the way galaxies cluster today. By measuring the size of these patterns at different times in cosmic history, scientists can determine how the universe's expansion rate has changed over billions of years. It's astonishing to think that the faint whispers of sound waves from the first few 100,000 years after the Big Bang still shape the structure of the cosmos today. And even more astonishing that by mapping those patterns, we can chart the future of everything. Each measurement, each light curve, and each redshift is a data point in a vast, unfolding story, a story that reaches from the first light of creation to the still expanding horizon of tomorrow. As the tools of observation have grown more sophisticated, our view of the cosmos has become clearer. The Hubble Space Telescope provided the first detailed measurements of distant galaxies and supernova, allowing astronomers to confirm that the universe's expansion is accelerating. Later, the WMUP and Planck satellites refined our view of the early universe, revealing not only the precise age of the cosmos, but also its composition. How much of it is dark energy, dark matter, and ordinary matter? And now, newer instruments like the James Webb Space Telescope and ground-based observatories like the Vera Rubin Observatory are reaching deeper into time, capturing the light of the first galaxies ever formed, bringing us closer to understanding how cosmic expansion evolved from the beginning until now. The act of measuring the universe is an act of both science and poetry. It requires not only instruments, but imagination, the ability to see meaning in light that has traveled across billions of years, to translate the faintest glow of a dying star into the rhythm of cosmic motion. Every photon carries information about where it came from and how far it has traveled, and by studying it, astronomers can reconstruct the past and forecast the future. When scientists talk about measuring the cosmic future, they do not mean predicting exact dates or specific events. They mean understanding the forces at work, the balance between gravity, matter, and dark energy, and how they determine what the universe will become. If dark energy remains constant, as the current evidence suggests, the universe will continue expanding at an ever-accelerating pace. Galaxies will drift apart faster and faster, until eventually, each will vanish beyond the other's reach, carried away by the expansion of space faster than light can travel. Stars will die, light will fade, and the universe will grow cold and silent. But these are projections based on measurements, the slow accumulation of evidence across decades and generations. The work of cosmology is an act of patience, where each new observation refines our view of the infinite. When astronomers measure the light of a distant supernova, they are looking across billions of years, effectively watching the past unfold in the present. They see the universe not as it is now, but as it was when that light began its journey, long before the Earth existed, before the sun was born, before life had any shape or name. One of the most haunting aspects of these measurements is that they show how limited our view truly is. The universe we can observe, the observable universe, is defined by the distance light has been able to travel since the Big Bang. Beyond that horizon lies more universe, perhaps infinite, but forever hidden from us because its light will never reach our eyes. As expansion accelerates, more and more of the cosmos slips beyond that boundary. What we can measure is shrinking in relative terms, even as the universe itself grows without end. There's a quiet irony in that. The more precisely we measure the universe, the more we realize how much of it we will never see. The instruments we build grow sharper, the data more detailed, yet the cosmic horizon retreats faster than we can chase it. Each new discovery expands our understanding, but also deepens the mystery, reminding us that we live within a universe too vast to ever fully grasp. And yet, we keep measuring. We keep watching, mapping, calculating. The future of the universe may be written in mathematics, but to study it is also an act of wonder. Each observation of a distant galaxy is an echo of time, a fragment of a story that began billions of years before humanity opened its first telescope. The cosmic expansion may continue forever, but our effort to understand it anchors us in the present, here, now. In this fleeting moment when the stars still shine and the universe's rhythm can still be heard through the soft hum of light. If you could listen closely enough, you might imagine that rhythm not a sound, but a kind of cosmic heartbeat, the steady pulse of space stretching, of galaxies drifting apart in silence. It is measured not in seconds, but in eons, not by clocks, but by the light of distant suns. And every measurement, every flicker of data, every trace of a redshifted star tells us that the universe is still moving outward, still expanding, still writing its own future across the fabric of time. If we want to understand when the universe might stop expanding, we must first understand what's driving that expansion in the first place. For most of cosmic history, scientists believed that gravity was the dominant force shaping the fate of the universe. Gravity pulls matter together, galaxies attract each other. Stars cluster in spirals, and black holes consume everything that ventures too close. For a long time, it seemed logical that, given enough time, the mutual gravitational pull of all the matter in the cosmos might slow the expansion and eventually cause it to reverse. The universe would collapse inward, perhaps ending in a fiery Big Crunch. But then came an astonishing discovery, one that changed everything we thought we knew about cosmic destiny. The realization that not only is the universe expanding, but that expansion is accelerating. Some invisible energy, is pushing space itself apart faster and faster. That mysterious something is what scientists call dark energy. The term dark energy is a placeholder, a name we give to something we don't yet understand. It doesn't refer to darkness in the sense of shadow or obscurity, but rather to the unknown. It's a label for the force or property or phenomenon that seems to make up roughly 68% of the total energy content of the universe, yet reveals itself only through its effect on cosmic expansion. We can't see it, touch it, or detect it directly, but we can observe what it does. It acts as a kind of anti-gravity, a pressure that pushes rather than pulls, a force that causes galaxies to recede from one another at an ever-increasing rate. The discovery of dark energy began with observations of distant Type Ia supernova in the late 1990s. Astronomers, including two independent teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees, were measuring the brightness and redshift of these stellar explosions to determine how the universe's expansion had changed over time. What they found was completely unexpected. The supernovae were dimmer than predicted, indicating they were farther away than they should have been if the expansion were slowing. Instead of decelerating under the pull of gravity, the universe was speeding up. This revelation stunned the scientific world and earned those teams the Nobel Prize in Physics in 2011. To explain the acceleration, cosmologists revived an idea that had once been discarded: the cosmological constant. First introduced by Albert Einstein in 1917. When Einstein formulated his equations of general relativity, they suggested that the universe should be either expanding or contracting. But at the time, the prevailing belief was that the cosmos was static. To make his equations fit that expectation, Einstein added a term, the cosmological constant, which represented a repulsive force that balanced gravity and kept the universe stable. Later, when Hubble's observations showed that the universe was indeed expanding, Einstein called the cosmological constant his greatest blunder. Yet, decades later, the very same concept returned as a way to explain the accelerating expansion, a kind of built-in energy of space itself that grows stronger as the universe grows larger. In modern cosmology, this cosmological constant is considered one possible form of dark energy. It suggests that empty space isn't truly empty, but has a constant energy density, a vacuum energy that exerts a repulsive effect. As the universe expands, new space forms, and with it, more of this vacuum energy. Unlike matter, whose density decreases as space expands, dark energy's density remains constant, meaning its total influence grows over time. This explains why the universe's expansion, once slowed by gravity, began to accelerate around 5 billion years ago. Dark energy had become dominant, overpowering the gravitational attraction of matter, but not all theories of dark energy rely on the cosmological constant. Some physicists propose that dark energy could be dynamic, a quintessence, an evolving field that changes over time. This idea imagines dark energy as something more fluid, perhaps related to fundamental quantum fields or unknown properties of spacetime itself. If this is true, then the behavior of dark energy could vary in the future. It might strengthen, weaken, or even reverse. That possibility opens the door to different fates for the cosmos, depending on how this mysterious force behaves in the long run. To probe dark energy, scientists have designed a new generation of experiments and telescopes dedicated to measuring how cosmic structures evolve over time. Projects like the Dark Energy Survey, the Euclid mission launched by the European Space Agency, and NASA's upcoming Nancy Grace Roman Space Telescope aim to map billions of galaxies, measuring their positions, shapes, and distances with unprecedented precision. By comparing how structures form and how light bends as it travels through space, astronomers can infer how dark energy influences the expansion and growth of the universe. The effect of dark energy is subtle on human scales, but overwhelming on cosmic ones. Imagine galaxies as points on an ever-inflating balloon. As the balloon expands, the galaxies drift farther apart, not because they are moving through space, but because space itself is stretching. On large enough scales, dark energy dictates that stretching, determining the rate at which cosmic distances grow. Over billions of years, this process isolates galaxies from one another. Light from distant galaxies takes longer and longer to reach us, and eventually, it will never reach us at all. Each galaxy will become an island universe, surrounded by an infinite darkness from which no new light arrives. What makes dark energy so mysterious is that it resists intuition. We are accustomed to thinking of energy as something that acts within space, a force that pushes or pulls objects. But dark energy isn't acting in space. It is a property of space. It exists everywhere, evenly distributed, without form or direction, quietly reshaping the geometry of the cosmos. It does not clump or gather like matter. It does not radiate or absorb light. It is as if the universe itself has a built-in tendency to expand, an internal pressure that drives it outward. Physicists have tried to connect dark energy to what we know from quantum mechanics, where the vacuum of space isn't truly empty but teems with virtual particles that flicker in and out of existence. These quantum fluctuations have an energy, and when summed across all of space, they could, in theory, produce a vacuum energy density, a cosmological constant. However, when scientists attempt to calculate this energy from quantum theory, they arrive at a number that is staggeringly larger than what we observe, by about 120 orders of magnitude. It's one of the greatest unsolved puzzles in physics, why the vacuum energy predicted by quantum theory is so vastly different from the dark energy we actually measure. This discrepancy is often called the worst theoretical prediction in the history of physics, yet it might also be a clue to something deeper, a sign that our understanding of the relationship between quantum fields, gravity, and spacetime is incomplete. In the grand equation of cosmic balance, dark energy plays the role of the invisible hand that shapes destiny. It determines not only how the universe expands, but also what kind of universe we inhabit. A universe dominated by matter would slow and eventually collapse. A universe dominated by dark energy, as ours appears to be, expands forever. The strength and constancy of dark energy's influence decide whether expansion continues smoothly, accelerates endlessly, or changes course in some unpredictable way. If dark energy remains constant, as the cosmological constant model predicts, then the universe will approach a state known as the heat death. Galaxies will drift beyond each other's horizons. Stars will burn out, black holes will evaporate, and the cosmos will settle into a cold, dark, and empty expanse. But if dark energy grows stronger over time, its repulsive force could eventually become so intense that it tears apart galaxies, stars, planets, and even atoms in a catastrophic event known as the Big Rip. Alternatively, if dark energy weakens or reverses, gravity could one day reclaim its dominance, halting the expansion and leading to a big crunch, a collapse back into a singularity from which a new universe might someday emerge. Each of these futures, heat death, Big Rip, or Big Crunch, depends entirely on what dark energy truly is and how it behaves. And that remains one of the most profound questions in all of science. We live in an era where we can measure the expansion of the universe, map its earliest light, and calculate its possible destinies, yet we do not know what 68% of it actually is. That irony lies at the heart of modern cosmology. We have never known so much, and yet, we have never been so aware of how much we don't know. The role of dark energy is not only scientific, but also philosophical. It challenges our perception of permanence, our understanding of balance, and our assumptions about the universe's purpose. It reminds us that the cosmos is not static, not eternal in the way ancient thinkers imagined, but a living, evolving entity driven by invisible forces. The very emptiness of space is not inert, it is active, dynamic, alive in its own quiet way. Every moment of cosmic time is shaped by the silent work of dark energy, pulling galaxies apart, rewriting the structure of existence. setting the tempo of the universe's infinite expansion. When we look up into the night sky, we are witnessing a living history of expansion. Galaxies rushing away from one another, space itself stretching in all directions. The question that naturally arises is whether this cosmic expansion will go on forever, or if it might someday come to an end. To explore this question, we must look at the fundamental ingredients that shape the universe's destiny: matter, dark matter, radiation, and dark energy. Together, they form a delicate balance between the pull of gravity and the push of expansion. The universe's fate depends on which side of that balance ultimately wins. Within a boundless multiversal expanse, the inflationary theory of the early universe gives further weight to this idea. Shortly after the Big Bang, the universe underwent an unimaginably rapid period of exponential expansion, driven by a high-energy vacuum state. This inflation smoothed and flattened the cosmos, explaining why it appears so uniform today. However, some models of inflation predict that this process never completely ends. While inflation stops in our region, it continues elsewhere, creating an infinite mosaic of universes. If this is true, then the observable universe is just a small pocket of a much greater reality, a single expanding bubble in a sea of eternally inflating space. But even without invoking the multiverse, the question of infinity versus finiteness carries profound implications for our understanding of existence. If the universe is finite, it might someday curve back on itself, perhaps leading to a big crunch, where expansion reverses and all matter collapses inward again. If it is infinite and expansion continues forever, then the cosmos will face an opposite fate, a heat death, where galaxies drift apart, stars burn out, and entropy reaches its maximum. In that distant future, space would be cold, dark, and nearly empty, with only the faint radiation of decayed matter lingering in the void. Expansion would continue endlessly, but meaninglessly, as everything becomes evenly spread across infinite space. The idea of infinity itself is both alluring and unsettling. In mathematics, infinity is not a number, but a concept, something that cannot be measured, counted, or contained. When applied to the universe, it implies that there are infinite galaxies, infinite stars, and perhaps infinite versions of ourselves scattered across the cosmic landscape. Somewhere in an infinite expanse, there could exist regions identical to our own observable universe, differing only in minute details. The infinite universe implies infinite possibility, but also infinite repetition. It challenges the uniqueness of our existence and the very definition of reality. Whether finite or infinite, the universe has no edge in the conventional sense. There is no wall, no boundary, no outer surface marking the end of space. The cosmos does not sit inside a larger void, nor does it expand into emptiness. Space itself is the framework of existence, and it defines what inside and outside even mean. Beyond that framework, those concepts dissolve. To say that the universe expands is to say that the distances between points of space grow larger, not that it occupies more territory. It's not an explosion, but a stretching of geometry, scaling of existence itself. This realization forces us to redefine what we mean by where. When we ask, where does the universe expand into? We are unknowingly assuming that space exists outside the universe. But space, by definition, is what the universe is made of. There is no beyond, because there is nothing outside the structure of spacetime. Space doesn't need a container any more than time needs a direction outside itself. The universe is self-contained, whether infinite or finite. It encompasses all that can exist. In the end, the debate between a finite and infinite universe remains open, shaped by both observation and theory. Our instruments can only probe so far, and our mathematics can only describe so much. What lies beyond our cosmic horizon may forever remain hidden, a mystery folded into the fabric of existence itself. What we do know is that the universe continues to expand. Not into something, but of itself, carrying with it the endless question of whether infinity is a destination or the eternal nature of reality itself. When we talk about the expansion of the universe, we are not just describing a current event, but also peering into its destiny. The fate of the cosmos is written into the rhythm of its expansion, a slow, steady breathing of spacetime that began with the Big Bang and continues into a future that stretches beyond imagination. If space expands forever, as current evidence suggests, then the universe is on a trajectory toward a lonely, cold, and ever-diluting existence. Yet within that distant fate lies a story that blends cosmic physics with existential wonder, a story of what it means to live in a universe that will never stop growing, never stop changing, and never truly end. The first clue to the universe's future lies in its past. When the Big Bang occurred about 13.8 billion years ago, the universe was unimaginably dense and hot. It expanded rapidly, cooled, and allowed matter to form. Gravity then pulled matter into clumps, forming galaxies, stars, and planets, the cosmic architecture we see today. For much of its history, the expansion was slowing down because of gravity. Every particle of matter pulled on every other particle, trying to resist the outward rush. For decades, scientists assumed that gravity would eventually win, halting the expansion and perhaps reversing it into a catastrophic collapse known as the Big Crunch. But in the late 1990s, something astonishing was discovered: the universe's expansion wasn't slowing down, it was accelerating. This acceleration is driven by a mysterious force called dark energy, which seems to act as a repulsive pressure inherent in the fabric of space itself. Unlike matter and radiation, which dilute as the universe expands, dark energy appears to remain constant, meaning that as more space comes into being, more dark energy is created. This discovery changed everything about how we think the universe will end. If dark energy continues to dominate, the expansion will never cease. The cosmos will continue to grow faster and faster, galaxies drifting apart at increasing speeds until even light cannot bridge the gulf between them. To understand this fate, it helps to imagine the large-scale structure of the universe as a cosmic web, a network of filaments composed of galaxies and dark matter, stretching across billions of light years. Right now, this web still holds together through gravity. Clusters of galaxies remain bound, and the Milky Way is part of one such cluster known as the local group. But over cosmic timescales, the relentless expansion will change this balance. In a few tens of billions of years, distant galaxies outside our local group will slip beyond our cosmic horizon. Their light will be stretched so much by expansion that it will no longer reach us. From our perspective, they will simply fade away, disappearing into the darkness as if the universe itself were turning off its stars one by one. As time progresses, only the galaxies that are gravitationally bound to us, the Milky Way, Andromeda, and a few smaller neighbors, will remain visible. Eventually, even those will merge into a single massive elliptical galaxy. Beyond it, the sky will be black. The cosmic web will unravel, not because the galaxies themselves move, but because the space between them grows faster than any signal can travel. The observable universe will shrink, not in size, but in content, as everything beyond our gravitational island vanishes over the horizon. The physics of this distant future can be traced through several stages. In the next 100 billion years, star formation will slow dramatically. The supply of interstellar gas, which fuels the birth of new stars, will be used up or expelled by supernova and galactic winds. The universe will enter an age of aging stars, long-lived red dwarfs burning dimly, illuminating sparse pockets of the cosmic night. Over trillions of years, even these faint stars will exhaust their fuel, becoming white dwarfs, neutron stars, or black holes. The night sky will darken further, and the temperature of space will continue to drop, as the cosmic microwave background stretches into wavelengths too long to detect. This gradual fading leads to what scientists call the degenerate era. During this time, the universe will be populated mostly by stellar remnants, white dwarfs slowly cooling into black dwarfs, dense spheres of carbon and oxygen no longer emitting light. Black holes will still punctuate the darkness, swallowing the occasional wandering object, but even they will not last forever. According to Stephen Hawking's theory of black hole evaporation, Black holes emit a faint radiation and lose mass over time. For the largest black holes, this process takes an almost unimaginable span, 10,100 years or more. But eventually, they too will evaporate, releasing their energy as the last flickers of light in an ever-darkening cosmos. If dark energy remains constant, the expansion will continue exponentially. The distances between all unbound objects will increase faster and faster. Galaxies will vanish from sight, stars will fade, and even atoms may not remain safe forever. Some cosmological models predict a scenario known as the Big Rip. In this hypothetical future, the repulsive force of dark energy grows stronger over time, tearing apart galaxies, then solar systems, then planets, and eventually in atoms themselves. Space would expand so violently that the very fabric of matter would unravel, leaving only a diffuse mist of energy scattered through infinite emptiness. However, the Big Rip depends on the precise nature of dark energy, which remains one of the greatest mysteries in modern science. If dark energy is constant, a cosmological constant, as Einstein once proposed, then the expansion will continue forever at a steady exponential rate. Galaxies will drift away, but atoms will remain intact. The universe will approach a state of heat death, also known as the Big Freeze. In this scenario, as expansion continues, all available energy becomes evenly distributed. No gradients of temperature or density remain to drive motion or life. Entropy, the measure of disorder, reaches its maximum, and the universe settles into an eternal stillness. As we drift to the end of this journey through cosmic time, the question that began it all still lingers softly in the air. If space expands forever, where does it expand into? We have traveled from the first trembling moments of the universe to the distant horizons of what may come, tracing the invisible threads of reality as they stretch beyond imagination. Along the way, we discovered that space does not expand into something else. It expands within itself. The universe is not a balloon rising into a void, but a self-contained fabric, unbounded and complete. It is a reality that grows without edge, a vastness that carries everything within it, including us. We have seen how galaxies drift apart, not because they are flying through space, but because the space between them grows. We have watched time slow and stretch as the universe expands, felt the quiet pull of dark energy as it drives everything outward, and glimpsed the distant future when the stars will fade, and the cosmos will cool into stillness. The expansion of space is not only a scientific truth, but a profound meditation on existence itself. It tells us that change is not a flaw in the universe, but its essence. That to be alive, to exist, to think, is to expand. In the endless unfolding of the cosmos, we are but a brief whisper, and yet within that whisper lies awareness. We are the universe made conscious, reflecting upon its own immensity. Every observation, every thought, every question about the stars is part of the same expansion, growth not of matter, but of understanding. The universe expands outward. The human spirit expands inward, reaching for meaning in the silence between galaxies. Perhaps that is what makes this cosmic truth so beautiful. The expansion of the universe mirrors the expansion of our minds. Just as space has no boundary, neither does curiosity. Just as the galaxies recede into the infinite, so do our thoughts stretch toward the unknown. We do not stand outside the universe, watching it grow. We are growing with it, carried within its breath, part of its eternal motion. And as you lie here now, breathing softly beneath the quiet ceiling of night, remember that every inhale mirrors the rhythm of creation. The air you draw in has drifted across centuries, through the atoms of stars, through the long history of expansion itself. You are made of the same universe you wonder about, built from its particles, shaped by its forces, sustained by its light. The universe expands forever, not into something else, but into itself, into possibility, into memory, into being. And within that infinite unfolding, your awareness, your thoughts, your very existence are part of its story. The cosmos is not out there. It is here, within you, expanding still in silence and wonder and endless becoming.